chapters 15 and 16. Chapter 15 is the nature of the solar system. I'll be covering chapter 15 in this video, and then on Tuesday I will upload the chapter 16 video, so you guys will have those all set to complete your assignments this week. So, before we start discussing the universe, we need to start looking at our evolution of understanding of astronomy. So, astronomy is one of the oldest fields of science. So early people observed their world very closely, and through these observations they noticed that the seasons tended to associate with the sun's position during the year. So like we talked about with the sun's rotation around, or the Earth's rotation around the sun. Sorry. The fact that stars and planets seem to move throughout the night sky. They also noticed that there was a very regular, predictable cycle of lunar phases, and you could predict arrivals of comets and meteors, along with eclipses of the moon and sun. So they tried to use these observations to understand and predict these cycles, sometimes attributing them to mystical forces or human-made events. These attempts to understand led to the science of astronomy, and the earliest written astronomical records are actually Babylonian, and they are from about 1600 BC, or approximately 3,600 years ago. Now, from about 600 BC to 150 AD, the ancient Greeks used philosophy and these observations to try and explain the movements of what are deemed heavenly bodies. They tended to hold a geocentric view of the universe, so this is very Earth-centric. This is where they viewed that the Earth was stationary in its point in space, and that it was at the center of the universe and everything rotated around it. Additionally, that stars were on a celestial sphere, which was a transparent hollow sphere that turned around the Earth. So the Earth was a ball contained within a much larger ball. And this larger ball is what contained all of the stars and planets. They were able to predict eclipses as early as 480 BC, so they became fairly accurate in some regards in their early astronomy. They knew the Earth was a sphere and measured its circumference to within less than 1% of modern measurements. This was based off of the astronomer Eratosthenes in 220 BC. So this is an example of the geocentric solar system model that the ancient Greeks came up with. So we have the Earth here, and they believed that the moon circled around the Earth, but that the next closest planet was actually Mercury, and then Venus, and then the Sun. So we had Mercury and Venus were actually closer to the Earth than the Sun, according to the ancient Greeks, followed by Mars, and then Jupiter, and then Saturn. They claimed there were 7 wanderers, or planetae, that orbited around the Earth. And in this, they're actually including the Sun as a wanderer. Next in the timeline of astronomy was the Ptolemaic system. This came about in 141 AD. This was also a geocentric model. And the Ptolemaic system used 2 motions for the planets to try and explain what we have that is our apparent retrograde motion. So this is where, apparent retrograde is where you get an apparent backwards movement of some planets against the night sky due to a combination of Earth and the planet's own motion around the sun. So you would have, for instance, Mars traveling across the night sky, and then all of a sudden it would look like it's moving back the way it came before continuing on its path. So to explain this, Ptolemy used the idea that there were 2 different motions planets made. They had large orbital circles called deferents and smaller circles called epicycles. So here is the geocentric model of the Ptolemaic solar system. So again, we have the Earth at the center and the moon rotating around. Again, Mercury and Venus are closer than the sun. But then as Mercury and Venus are moving around the Earth, they're also moving in these smaller epicircles, which gives us that retrograde motion. Here we go. I'm going to post a link to this video. This is a really, really great video to demonstrate the apparent retrograde motion and just how that appeared to early astronomers and why this deferent circle and epicycle circles were the best solution they could come up with given their knowledge. So take the time to watch this video. I think it's about 5 minutes long, but it explains it really well. It's a really great graphical representation of the concept. So Ptolemy's model and his theory were preserved in the Middle East and translated into Arabic after the fall of the Roman Empire. And his work was reintroduced into Europe somewhat later and became scientific dogma to explain how creation worked. So how does the Ptolemaic model of the solar system follow the scientific method, and how does it fail the scientific method? Okay, so I kind of want you to think way back to the introduction. What are the steps of the scientific method? How does this model really follow these steps? You make an observation, you develop a hypothesis, you test your hypothesis, and then you come to a conclusion. So where along that kind of thought process would this model have failed? So it is based on observations and involves a hypothesis, and it has a testable explanation. Now, where it fails is in the real world and modern observations and measurements, the hypothesis is disproven. So given their measurement capabilities at the time, it followed the scientific method. However, given our advances in science and technology, we are now able to disprove it. So because it can be disproven with modern observations, that is where it fails. Now we move on to modern astronomy. Nicholas Copernicus is believed to be basically the father of modern astronomy. He actually concluded that Earth was a planet, and he constructed a model that put the sun at the center and continued to use circular orbits for the planets, which still caused problems in predicting planetary motions. It challenged the primacy of Earth in the solar system. So he's really the one who challenged the idea that everything rotated around us, everything moved around the Earth. We were no longer literally the center of the universe. Next was Tycho Brahe. I'm unsure on how to pronounce this man's name, sorry. But he made and recorded precise observations of the movement of stars. And he tried to find the stellar parallax, the apparent shift in a star's position that would have to occur if the Earth traveled around the sun. So he did not accept Copernicus's idea because he was unable to observe this stellar parallax. However, the parallax does occur, but it is too small to be measured without telescopes, and that was not a tool he had at the time. So the stellar parallax has actually been proven with the advent of modern technology, but it was not something he was able to observe and measure in his time, and he used that as a basis for disproving the Copernican model. Johann Kepler ushered in the new astronomy. He basically built on Copernicus' idea that planets revolved around the sun, but expanded on this with 3 laws of planetary motion: that the orbits of planets are elliptical, not circular, that the planets revolve around the sun at varying speeds, and that there's a proportional relation between a planet's orbital period and its distance to the sun. And the distance to the sun is measured in astronomical units. 1 AU averages about 150 million kilometers, or 93 million miles. So here's a video on Kepler's law. Again, I will post this video for you. Next, probably another one we've all heard of, Galileo Galilei. So he strongly supported Copernicus' theory. He used experimental data to try and support and prove this idea. He actually constructed a telescope in 1609, and through this telescope he observed 4 moons around Jupiter. That planets appeared as circular disks, not just points of light. And phases of Venus showing Venus actually orbits its source of light. He is also able to distinguish features of the moon and sunspots. Now, Galileo was prevented from widespread distribution of his theories due to the confliction with the accepted church teachings during his life. The church was still very geocentric or earth-centric at the time. The Earth was the center of the universe. Everything revolved around us. They were not open to any ideas that challenged this. However, his works were eventually published with the approval of the church. Sir Isaac Newton developed the law of universal gravitation, that every body in the universe attracts every other body with a force proportional to their mass and inversely proportional to the square of the distance between them. And if you guys remember back to high school physics, this is something we talked about. He proves that the force of gravity, combined with the tendency of a planet to remain in straight line motion, resulted in the elliptical orbits discovered by Kepler. His law of universal gravitation allows us to calculate planetary orbits, speeds, and rocket trajectories needed to rendezvous with other planets. And it also allows us to calculate the mass of planetary bodies and therefore calculate their density. Ooh. There we go. So here we're looking at an example of this universal law of gravitation. So we have a planet and it wants to move in a straight line. Okay, so that's this line here. However, you've got the sun's gravitational force trying to pull this planet directly towards it. So because you've got this force pulling inward and the planet's tendency to move in a straight line, it actually ends up pulling it in this elliptical orbit based on the difference in the forces between the gravitational force and the straight line trajectory. Now to move on to the actual formation of our solar system. The current overriding idea of how our solar system was formed is called the nebular theory. This states that the planets formed about 5 billion years ago, and the solar system condensed from a solar nebula, which is a rotating cloud of gas and dust. It states that most material collected at the center as the hot protosun. Other material formed a flattened rotating disk around the protosun, and as the matter in the disk cooled and collided, they formed planetesimals. These planetesimals continued to collide and grow larger to form protoplanets. The protoplanets closest to the sun were made of materials with high melting points, metals and other minerals. And the protoplanets further from the sun were made of materials with low melting points, and so they existed mainly as gas and ice. So this just shows the solar nebula, nebular cloud, and you start to get this rotating disk around the protosun. And then as the sun solidifies, this flattened disk starts to collect. You see the material starting to really attract to each other, collecting into these very defined orbits where they start colliding and accumulating until they develop into protoplanets and then full-blown planets. As the protoplanets formed, the materials that composed them separated. The denser metallic elements sank towards the center, and the lighter elements migrated towards the surface. This process is called chemical differentiation. Due to their surface gravities, Venus and Earth also managed to retain atmospheric gases. And then due to the cold temperatures, the Jovian planets, so the outer planets, contained a higher percentage of ices, or solidified gas, such as ammonia, methane, carbon dioxide, and water. There are two groups of planets in our solar system. The terrestrial planets, these are the ones that are more Earth-like. They are smaller, dense, and rocky with low escape velocities. These are Mercury through Mars, or the inner planets. The next are the Jovian or Jupiter-like planets. This is Jupiter through Neptune. These are massive with low density and gaseous. They have thick atmospheres of hydrogen, helium, methane, and ammonium, and very high escape velocities. Pluto and other dwarf planets are not included in either group, because Pluto has since become not a planet again. I think it's gone back and forth. Pluto is no longer a planet. It is classified as a dwarf planet, which we will not discuss in this chapter. So the two planets are divided in part because of their relative distance to the sun. There's an asteroid belt that moves between the inner and the outer planets, but also because their compositions are so very different between the two groups. So we have our terrestrial planets, which have that outer rocky crust. They have a rocky mantle with a metallic core and an inner metallic core. As far as scientists are aware, Earth is the only one with a secondary inner metallic core, although it is possible that Venus or Mars could have one. And the moon is actually categorized, when we talk about structure, as a terrestrial planet because its composition is so similar to the actual terrestrial planets. Okay, the Jovian planets have visible clouds, then a next layer of the gaseous hydrogen or helium, followed by liquid molecular hydrogen, followed by liquid metallic hydrogen, and finally a rocky or iron core. So that's Jupiter and Saturn. It's believed that Uranus and Neptune do not actually have that liquid molecular hydrogen or the metallic hydrogen. They go from the gaseous hydrogen helium to ices to their rocky core. Oops. So this is showing the solar heating or the temperature and the relationship to the gravity of these planets. So airless worlds have relatively warm surface temperatures or weak gravities. And then bodies that have atmospheres, bodies with significant atmospheres have low surface temperatures and strong gravities. So here we're looking at Neptune, Uranus, Saturn, and Jupiter. They all have much higher gravity and lower solar heating temperatures. Earth has an atmosphere, it has a middle of the road gravity, and a higher solar heating or solar temperature. Now, planetary impacts, these are common during the formation of planets and actually provide clues into the early history of our solar system. They are less common today because most of the material has been swept from the orbits by the planets. But these impacts leave craters, and these craters are found on all terrestrial planets and their moons. They are also found on many of the moons of the Jovian planets. The crater density and cross-cutting craters are useful guides to relative ages of the surface of planets. So we actually use some of our Steno's laws to determine planetary formation because of these crater impacts on specifically the moon and on Mars. So here's an image of the lunar surface. So based on crater density, which side of the photo has a younger surface? Where do you find examples of cross-cutting craters, and which crater is older in each case? And then why are so few craters on Earth even though it is a larger target than the moon? So here we've got a region that's pocketed with craters all over. And then we have a region here that looks fairly smooth, very few craters. So it would be understood that this smoother area is probably the younger side of the moon. It's got less impacts. It did not exist during this period of high celestial material movement. And then if you look, let's find a good example. Specifically right here, we've got a crater, and then we've got a smaller crater impacted on the side of it. So this larger crater was the one that existed first before having a smaller one impacting on part of the outer edge of that crater. So why would there be fewer craters on Earth even though it's a larger target than the moon? So first we need to discuss more features of the moon to answer this question. So a few of the characteristics, the diameter of the moon is 3,475 kilometers, which is actually unusually large compared to its parent planet. Most planets that have moons, there's a much larger size difference. They're usually much, much smaller than our moon is. Our planet is 3.5 times the density of water. Earth's density is 5.5 times that of water, so it's less dense than Earth. And it is comparable, but not exactly the same as Earth's rocks. It is thought that the moon has a small iron core, but that has not been proven, and has 1/6 the gravitational attraction of Earth. The moon has no atmosphere, and tectonics that may have existed are no longer active. The surface is bombarded by micrometeorites, which gradually make the landscape smoother. So it's like sandblasting something. So the consensus is that the moon formed as a result of a collision. It's believed that a Mars-sized body collided with the semi-molten Earth about 4.5 billion years ago, and some of the debris actually coalesced to form the moon, which is why the moon has similar composition but not identical composition to the Earth. It formed before the Earth had completely solidified and finalized its formation, so it hadn't reached its final composition yet. The impact model is consistent with the moon having a smaller core and lower density than the Earth. The lunar surface is broken up into two types of terrain, the Maria or Mar, Latin for sea. This is a dark region with fairly smooth lowlands and is believed to have originated from asteroid impacts and lava flooding. Second are the highlands, which are densely cratered regions that make up most of the moon. In fact, make up almost all of the backside of the moon and is much older than the Maria. So here we're looking at another picture of the Earth's moon. So we've got the lunar highlands. This is the earliest lunar crust, about 4.4 billion years old. So here we've got lunar highlands right here. And you can see it's very pocketed by craters, much older material. And then we've got the lunar maria, so the Mare Imbrium, the Sea of Rains, the Mare Tranquillatus, Sea of Tranquility. And these are areas filled by basalt flows, so about 3 to 3.5 billion years ago, which we believe is evidence of volcanism on the moon. Finally, we have large rayed craters, for example, the Copernicus crater right here, and that formed about 1 billion years ago. The U.S. lunar manned missions Apollo 11 through 17 landed in these areas. So we had one landing on right at the edge of the Mare Tranquillatus. We have 16 landing in the lunar highlands. 12 and 14 are near two ray craters. And this really gave us a good insight into the actual surface of the moon, and able to test the lunar material directly to compare it to composition of Earth's crust. So the lunar regolith covers all the lunar terrains and is gray, unconsolidated debris, primarily composed of igneous rocks, breccia, glass beads, and fine lunar dust. So you remember igneous rocks are those that are formed from lava or magma. And then breccia is actually a sedimentary material that is formed from the weathering of an igneous rock. The pieces weather off and then are reconsolidated. And here's a video on the origin of the moon. Mercury is the next planet we'll talk about. So Mercury is the innermost and second smallest. It has no atmosphere. It also has cratered highlands and smooth terrains. It is very dense and revolves quickly around the sun, 88 days, but rotates slowly. 176 Earth days is one Mercurian day. So a year on Mercury actually covers 2 years on Mercury equals 1 day on Mercury. So it will go around the sun twice in the time it takes it to complete one full rotation around its axis. It has extreme temperatures of 173 to 427 degrees Celsius. Next is Venus. This is second to the moon in brilliance, as seen from Earth. It is similar to Earth in size and density. Its orbital year is 225 Earth days, so it's about 2/3 of an Earth year, and rotates slowly. 1 day on Venus is about 244 Earth days. So here we've got 1 year is the same length of 1 day on Venus. It is covered in thick clouds with an atmosphere that is 97% carbon dioxide. And the atmospheric pressure is 90 times that on Earth. This has caused an extreme greenhouse effect, which means that the surface temperature averages 450 degrees Celsius during the day and night because of the insulating effect of the atmosphere. Venus has more than 1,000 active volcanoes that are greater than 20 kilometers wide, and those are just the ones that we know of. Next is Mars, the red planet. This has half the diameter of Earth. 1 orbital year is 687 Earth days. It has a much thinner atmosphere than Venus, but it is 95% carbon dioxide. The atmospheric pressure is only 1% as dense as Earth, so it's much lighter atmospheric pressure. It has cold temperatures up to or down to negative 140 degrees Celsius near the poles to 68 degrees Celsius at the equator during their summer. The polar caps of ice are covered by frozen carbon dioxide, and the planet has dust storms with winds up to 170 miles per hour. Its axis of rotation actually tilts at a 25-degree angle. It is not completely vertical, and there are no plate tectonics on Mars. So looking at the two hemispheres of Mars, 2/3 of the surface is cratered highlands, and it has some of the largest volcanoes in the solar system, including Olympus Mons, which is believed to be the largest volcano, and it supports the idea that there are no plate tectonics on Mars because it has developed into such an expanse because it resides over a hot spot and never migrates away from it. The dominant force of erosion today is wind. However, there's evidence that wind and water were the major erosive agents in the past. And poleward of 30 degrees, water ice is found within 1 meter of the surface. So if you move about 30 degrees towards either pole, you start to find water ice. So here's a picture of the caldera of the Olympus Mons. And this is showing evidence of rounded gravel in a conglomerate. So I talked about breccia is that sedimentary rock of weathered igneous that consolidates and is cemented. And if you remember back from chapter 3, breccia is similar to conglomerate. It's a rock made up of other rock pieces. Breccia is very angular in shape, whereas conglomerate has pieces that are very rounded in shape. Now the rounded shape pebbles in conglomerate indicate water weathering. Water tends to smooth and round out these materials. So that combined with aerial images that look like abandoned stream beds really support the idea that at some point in time there was water on Mars's surface. Next we're going to move to the outer planets. First we're going to talk about Jupiter. This is the 5th largest from the Sun and is very massive. It's about, if it was 10 times larger, it would be the same size as a small star. It has a very rapid rotation, less than 10 hours. And it has a banded appearance because of geostrophic winds. So these are very geographically contained bands of storms or winds. The Great Red Spot is actually a counterclockwise rotating storm. The surface is believed to be an ocean of liquid hydrogen. However, we have no way of proving that currently. And the core is believed to be metallic hydrogen. And Jupiter has at least 28 moons, 4 of which were discovered by Galileo. Of Jupiter's moons, Io is one of only 3 volcanically active bodies other than the Earth known to exist. So we have active volcanic activity still going on Io. Europa is the smallest of the Galilean moons. It has an ice surface that is crisscrossed by linear features. Ganymede is the largest and exhibits cratered areas, smooth regions, and areas covered by numerous parallel grooves. And Callisto is the outermost of the Galilean satellites. It is densely cratered, very similar to our moon. The 6th planet is Saturn. Again, it's similar to Jupiter in atmosphere. The rings are the prominent feature of Saturn. Saturn was discovered by Galileo in 1610 and composed of small particles that orbit the planet. The rings are composed of small particles that orbit the planet. The origin of the rings is still debated. Some believe it is the remnant of destroyed moons and material ejected from current moons. It has a dynamic atmosphere similar to Jupiter, and it has 30 named moons. Titan is the largest moon and has substantial atmosphere, 99% nitrogen. And Enceladus is icy but tectonically active. Uranus is the 7th from the Sun, nearly identical to Neptune. This one rotates on its side, so most planets have a vertical and near vertical axis and they rotate around that. Uranus has a near horizontal axis and rotates around that, likely due to a collision with an Earth-sized planet very early on in its history. It also has at least 10 rings, and its innermost moon, Miranda, is geologically active. It's believed Miranda has an internal heat source similar to the Earth. This is a look at Uranus's moon, Miranda. Neptune, the 8th planet and currently the last, also has a dynamic atmosphere. It is one of the windiest places in the solar system, with speeds of up to 1,500 miles per hour. It has a great dark spot, and you can see white cirrus-like clouds over the planet's surface. It has 5 faint known rings and 13 known moons. The largest moon is Triton. Triton orbits in the opposite direction of all planets, making it likely an object captured by Neptune's gravity and not actually an original moon. So it was most likely material traveling through space that got drawn in by Neptune. It has the lowest surface temperature in the solar system and volcanic-like activity with icy magma composed of water, methane, and ammonia. So here we're looking at Triton. So we've got geyser and plume activity. And these plumes give us an idea of potential wind direction, because as these geysers shoot up material, that material is going to fall straight back down to the surface of the moon unless you've got another force acting on it. So the fact that all of these plumes seem to be moving in a northeast direction, based on how we're looking at the picture, in a northeast direction, indicates that there is an active wind on that moon. There are also smaller bodies within our solar system. So I mentioned earlier the asteroid belt. This is the collection of asteroids that moves between Mars and Jupiter. These are small bodies. The largest is Ceres and is about 620 meters in diameter. Some have very eccentric orbits. They're not all regular elliptical or circular orbits. And many of the recent impacts on the moon and Earth were collisions with these asteroids. They are irregular shaped and they have varying composition, which makes it very difficult to determine their origins. Comets are often compared to dirty snowballs. Comets are composed of frozen gases and rocky and metallic materials. And as a comet moves near the sun, the gases vaporize to create the glowing head and tail. Again, the origins are not well known. The only thing that we know are that they formed far from the sun. One of the most famous comets is Halley's Comet, with a 76-year orbital period. So this shows an orientation of a comet's tail as it orbits the sun. So as it moves towards the sun through its orbital rotation, you see its tail kind of streams out behind it in an angle that's 90 degrees from the sun. So you've got 90 degrees, tail goes 90 degrees, but it's also got a portion of the tail that actually curves because of that orbital motion. So you've got a portion of the tail that's always at a 90-degree angle, and the rest of it curves out because of that orbital motion around the planet, or around the sun. And it starts to get this dust tail, or that curving tail, as it gets closer to the sun. So out here it's only got an ion tail, that 90 degree, and as that orbit brings it closer, you start to get your curved dust tail, which is that material that's being released from the ice as it is melted by the heat from the sun. Meteoroids, also called meteors when they enter our atmosphere. A swarm of meteors would be called a meteor shower. These are typically associated with a comet's path, and they are called meteorites when found on Earth. Meteorites are typically classified by their composition. Iron meteorites are mostly iron with 5 to 20% nickel. Stony are silicate minerals with the inclusions of others, and then stony irons are mixtures of the two. We obviously got very technical with the naming of these. Carbonaceous chondrites are rare, composed of simple amino acids and other organic material, which we think may give clues to the composition of Earth's core. Finally, the dwarf planets, which is a new category that was created the last time Pluto got the boot. So the most well-known dwarf planet is Pluto, with a diameter of 2,300 kilometers. This is about a fifth of Earth's diameter and less than half of Mercury's. It has a thin atmosphere, and its orbit path is eccentric to the orbit paths of the planets. Greater than 1,000 Kuiper belt objects were discovered as a second asteroid belt located at the outskirts of the solar system. These are rich in ices with physical properties similar to those of comets, and many other planetary objects are thought to exist in this belt. Dwarf planets orbit the sun, but they do not have enough gravitational force to sweep their orbital paths of debris, and there may be many dwarf planets within this Kuiper belt. So this shows you Pluto and its moon Charon, and just comparison, here's Pluto in relation to Earth, and even in relation to our moon. And this is the Kuiper belt, the outer part of the solar system, and here's Pluto's